So in the previous video, I've shown you guys that this series diverges to infinity. And the main thing that I was trying to show is that if you take the limit as n goes to infinity of an, if this is equal to 0, you really cannot draw any conclusion. Because for this example, we have seen that this limit gives you 0, but the infinite series diverges to infinity, right? And in this video, I will also like to show you guys an example that if you take the limit as n goes to infinity of an, that gives you 0, but the infinite series actually converges. So let's have a look. Last time I showed you guys the classic proof. If you haven't seen that, go ahead and check out the previous video. The link will be in the description. This time, we will do integrals. Have a look. We have the series of 1 over n, which means all that, right? And I'm actually going to consider a function 1 over x first. So that's how the graph looks like. Something like this. This is y equals 1 over x. And let's say here is 1, 2, 3, 4, and so on, so on, so on. Now, we'll be doing the area argument. Have a look. When x is equal to 1, if you go up, 1 over 1 is 1, so the y value here is 1. Good. Now, it looks like we have two choices to draw our rectangles. The first one is you can draw it like this, or the second one is you can draw it like this. I did it the second way because later on you'll see that the blue area, the area under the curve, is infinity. If you can show something that's bigger than infinity, then you get to draw the conclusion that this thing must also be infinity. If you show this right here is less than infinity, you really cannot say anything because maybe you have a smaller infinity than that. So that's why this time I'm actually putting down the rectangle above. I want to have the extra room right here. So right here you can see that the width is 1, the height is 1, so the area here is 1. And then continue, you put 2 into the x, so you get 1 over 2, and you're just going to draw a rectangle like this. The area of this rectangle is 1/2. Do the same thing. Here you get 1/3. And then if you continue, you get 1/4, and so on, so on, so on. So have a look. Based on the rectangle, the area argument, if you add up all the areas here, you get 1 plus 1/2 plus 1/3 plus 1/4, which is this. You can conclude that it must be greater than the area under the curve, which is the blue portion that I'm shading right now. And how do we compute the area under the curve? Integrals, right? And in this case, it will be the integral, you start with 1 to infinity, and the function is 1 over x. Can we integrate this? Sure thing. This integral is equal to ln x. You don't need absolute value because everything is positive. Plug in infinity, plug in 1, and you subtract. Ln of infinity is infinity. Ln 1 is 0. So we conclude that the result is infinity. Now have a look. This integral is infinity. This series is bigger than this integral, which implies that this series is bigger than infinity. So we can conclude that this series must also be infinity, which diverges. Done. Now, we'll be doing the same thing for the second series, which is the series of 1 over n squared. Notice, this time that if we graph 1 over x squared, the curve actually will approach the x-axis much faster. My picture is not the best, but if you look at the values, for example here, 1 over 16 is much smaller than 1 over 4. Okay, I still have 1, 2, 3, 4, and so on, so on, so on. And this time, we have to draw the rectangle carefully. 1, if you go up, you have two ways to draw the rectangle. Either to the left, either to the right. If it's to the left, the area will be less than the area under the curve. If it's to the right, the area will be more than the area under the curve. This time though, the way that we are going to draw it is actually under the curve. like this. Why? Because later on, you will see that the area under the curve from here to infinity is actually finite. In this case, you hope to show that this series is less than a finite number so that you can conclude that this is also going to be finite, assuming positive comparison, of course. That's why. Anyways, if it's 1 plugging, 1 square is 1, 101, so this is 1, the area here is 1. If you have 2, plugging is 1 over 2 square, which is 1 over 4 right here. And then do the same thing. This is 1 over 9, and then 1 over 16, which is very tiny already. So you can kind of have the idea why this right here will actually give you a convergent value, a finite value, right? It converges. Now, this is how we are going to make a comparison. Notice that we have the 1 right here, right? I'm actually not going to start with my integral with the 1, because if I do the integral with this rectangle in mind, I will have to integrate from 0 to infinity. That's not what we wanted, right? We don't want to integrate from 0 to infinity. Many reasons, if you integrate this from 0 to infinity, it's a divergent integral. You get infinity. That's not what we wanted. So don't look at the 1. Don't look at the 1. I just want to look at these right here. Okay, these right here. 1 and 1, same thing. Okay, fair comparison. I want to compare these, and you can see that these right here is going to be what? Less than the blue area that I'm shading right now. And how much is the blue area? You have to integrate it from 1 to infinity, and we have 1 over x squared, which is the same as x to the negative 2. And let's compute it real quick. Add 1 to the power is negative 1 divided by the new power. So we get negative x to the negative 1, and we go from 1 to infinity. So this right here, plugging infinity, is 1 over, it's negative 1 over infinity. Right, this is the same as 1 over x, plugging infinity. And then we have to subtract, plugging 1. Negative 1 over infinity is 0. And what's this? Negative 1. So it's 1. Have a look. What we are saying is that here we have 1. And here we have something that is less than 1. So we can conclude that this right here is less than 2. And because all the terms are positive, we know that this result has to be greater than 0. Therefore, you can see that this infinite series must converge. But now the issue is that, do we know the value that it converges to? In fact, based on this reason, we do not know, because definitely don't say this is equal to 1. No, because we have all the extra area, right? So if you add this up, it's not equal to 1. As a bonus, for the people who are still watching, I will tell you, this right here is a famous question. It converges to a very nice result. Pi squared over 6. Yeah, we don't do this in Cal 2, but it's a very nice result. You can keep in mind, you can impress your Calculus 2 teacher. Now, coming back here a little bit. Imagine if you integrate it from 0 to infinity, I'll tell you that integral will be infinity. Now think about it. If you show this whole thing is less than infinity, can you conclude anything? No, because you may just have a smaller infinity that's less than infinity. Maybe still diverge, you don't know. You can only conclude that this is also finite if you make a comparison that this is less than a positive finite number. Just like that. Okay? Hopefully this really helps. That's it.